Angular speed and momentum. When we talk about the Earth and its spinning, there is a lot of talk about it spinning at 1,000 miles an hour. Okay? There's truth to that, although it really isn't very significant. That's not how we perceive things. So we talked about somebody standing on the North Pole. If they're on the North Pole, they are rotating as opposed to be over his head, kind of does not look like it. They're rotating at a rate of 1 revolution per 24 hours. In a car, we talk about RPM. That would be revolutions per minute. Your car idles at about 1,500 revolutions per minute. 1 revolution for every 24 hours is actually very slow when we're talking about the angular speed. Here we have the merry-go-round again, and I'll draw the person hanging on. And then we also have somebody standing in the very center who is simply going around in circles. So we said in 101 that this person, in my opinion, will not be able to feel the rotation. The rotation is so slow that he won't feel it. Now, if he stands there long enough, he might notice that his scenery changes, but he probably cannot feel it. So he is going around once every 24 hours. So if we break up into quarters, he's going around this way. This chunk is 6 hours. 6 hours, 6 hours, 6 hours makes the 24 hours. He's going around in a circle like this, standing in the center of the merry-go-round or at the North Pole. This is 90 degrees. He turns 90 degrees in 6 hours. 90 divided by 6 is 15. So it's 15 degrees per hour. That is the angular speed. Angular speed is given in units of rotation, which might be 1 revolution, or in degrees per unit time. 15 degrees per hour is actually a very slow angular speed. The Space Needle in Seattle has a restaurant up at the top, and it turns. There is the outer ring of the restaurant next to the windows that turns, and the tables are set. This might be hard to see. The tables are set out here on the ring, so that while you're eating your meal, you can actually see the scenery change. This outer ring turns once per, so here I'm drawing a radii. The Space Needle restaurant turns 1 revolution every 47 minutes. 1 revolution is 360 degrees. Let's divide this out. 360 divided by 47 is 7.65. We'll say 7.6 degrees per minute. People sit and eat a meal traveling at 7.6 degrees per minute. Compare that to the person standing on the North Pole. The most common error in physics has to do with the conversion between units. In this case, we have degrees per minute and degrees per hour. If we want to compare them, we have to make the units the same. So we could turn this one into degrees per minute, or we could turn this one into degrees per hour. Now, in general, it is easier to make your numbers larger by multiplication than it is smaller by division. If we wanted to turn this into degrees per minute, we would need to divide it by 60. So then we would get a decimal over here. If we wanted to turn this one into hours, we would say it turns 7.6 degrees every minute. So after 60 minutes, it will have turned how many per hour. And the best way to do this we learned in high school chemistry and then on into physics. So we have 7.6 degrees, and I'm going to write it over minute, or 1 minute. And we need to multiply it by a conversion factor, and a conversion factor is actually equal to 1. So how many minutes are in an hour? There are 60 minutes in 1 hour. So this conversion unit right here, in parentheses, this is equal to 1. 60 minutes is the same as 1 hour. Whenever we multiply something by 1, it doesn't change. We're changing the way it looks, but we're not changing its value. So what is 7.6 times 60? I get 459.6. 459 degrees per hour. Now these are the two that we are comparing. 15 degrees per hour, which is somebody standing at the North Pole. 459 degrees per hour, which is someone sitting and having lunch in a Space Needle restaurant. The question is, can they feel it? They're spinning 30 times faster than someone standing on the North Pole. They're eating their meal and spinning 30 times faster. Do you think that the water in their cups is sloshed over at an angle? Do you think that if they set something round down on their table that it will roll off to the side toward the outside of the spinning restaurant? No. Turning once every 47 minutes, they can see the change. They can look out and notice that the scenery looks different than the last time they looked. But no, they cannot really feel it. Otherwise, it would be pretty complicated to carry a dish, a plate, from this inner ring, which is not turning, over into the part that is turning. It would be like jumping on a moving sidewalk from the side. So angular speed is how fast we turn per time. It can be given in revolutions or in degrees per unit time. Momentum has to do with once you have things turning, they have a certain momentum, which means it takes a certain amount of energy to stop a spinning merry-go-round. If you grab onto one of these handles, it will jerk your hand. So we both have momentum with a speeding car in a straight line and with things rotating. Moving on, centripetal force and acceleration. So before, we didn't do any mathematics, and we'll do that now. So we want to talk about this guy here. So I believe we have established that standing on the North Pole, you will not have any sensation of motion. I was on a plane yesterday. And if there wasn't turbulence, if the plane wasn't changing direction or bouncing up and down, I could almost imagine I wasn't in motion. Because we don't feel motion, we feel changes, we feel acceleration. So let's talk about this guy, because there is the very common 1,000 miles an hour, miles per hour, that we hear. How do they get that? Well, I will use rough figures here. If I will draw the Earth as looking down from the North Pole, rotating this way, the radius of the Earth, I'll say is 4,000 miles. So the radius is 4,000. The circumference, or the equatorial distance, is going to be 2 times pi times the radius. And in this case, that's going to be 2 times pi times 4,000 miles. And in that we get 25,132. And for simplicity's sake, I will round that to 25,000 miles. So the radius is 4,000 miles, the circumference 25,000 miles, and how quickly does it turn? Whenever we have a speed or a rate, it is a distance covered divided by time. So on this we are going 25,000 miles every 24 hours. Well, if that was 24, 24,000 divided by 24 is exactly 1,000. In this case, it's a little bit more. So 25,000 divided by 4,000, 24 hours, is 10,1041 miles per hour. Most of the time, we talk about angular speed. That's how quickly you're turning. Sometimes we do talk about this linear speed or tangential speed. A tangent, just to review, is a line or a line segment that touches a circle or a curve at exactly one point. If I put my pencil on this circle and then bring the ruler to guide me, there's a tangent. In theory, by definition, it touches at exactly one point. We'll say it's going this way. Sometimes it is important to talk about this linear speed or equatorial speed or tangential speed. Now, when it matters is the size of tires. We're really not interested in how fast tires turn per unit time. We're interested in how fast their linear speed is, because that is actually what your speedometer will say. So we have shown that the blue man here is going around the equatorial linear speed of about 1,000 miles an hour. But the question is, can he feel it?